actually also look at this way. Oh, no, right, because this part of it, because this part. So we actually could look at the same things in this, but because we want to compare cases, we actually want to plot it in Excel. So we can look at the pressure distribution. So it basically starts out with minus 100 centimeters, and then there's water input rates. Now we have the different observation nodes. So in 26 centimeter depth, it starts rising until the system is completely saturated. And the completely saturated system is actually a flux equivalent to -1. Then, of course, it takes some time until the wetting front or the infiltration front reaches 50 centimeter, and then it also goes up until the soil is saturated until we reach 0 pressure. We also can use, we can look at water content. So this is basically the same thing we just plotted. The only really thing I want to do is in Excel because we want to compare different cases in the same plot, which we can really do in HYDRUS. Then we also can look at fluxes. So it starts out with a very high flux, and then it basically gets as the system gets saturated, it gets actually more negative, means smaller value. This is right normal. I think I'm confusing a few things here. But negative flux means flux is going into the soil profile. And since initially we basically, the soil is dry, so the flux is higher, and then as the soil wets up, the flux should get smaller or higher. So is it a larger negative number? Is this a smaller flux or a higher flux? It's a higher flux. So it actually is the soil, a little bit of brain freeze. Of course, as more and more soils get filled up, you get from unsaturated hydraulic conductivity to full saturated hydraulic conductivity. So the flow cross section gets bigger and bigger, so actually the flux increases. So this is, I think, what happens here. This is basically what we also saw like in our plot. This we have for the observation nodes, but we basically can also look at this for the surface boundary fluxes. So we can look at actual surface flux. So this is basically what we just plotted. So it goes from, why is this one tilted here? So we start out.
Infiltration rate should be higher at the beginning.
No, we start out with a small soil profile, with a dry soil profile or a partially wet soil profile. And then we apply water to the surface at zero pressure head. So water starts infiltrating, increasing the moisture content layer by layer. And there's actually the moisture content increases layer by layer. So once we are saturated, we actually generate surface runoff. So the flux actually goes down. This is what happens here. And in the observation nodes, you basically see like an increase. So initially it's dry, then we add water, and then we add water, and then we add water, until it basically gets a stable value. So there's a difference between the observation nodes and between the surface nodes. Then we also can, for example, print the soil hydraulic properties. So if we close this to understand this in terms of the soil water characteristic. So pressure head versus water content, we can modify this actually. We can actually change this so that we have this typically, so we can actually plot the water content on the horizontal axis and the pressure head on the vertical axis. Then we can kind of change this to log scale. So we go to axis, y-axis, select. So we can change this to a log scale. If we apply this, then we don't want to go all the way up, so we want to change maybe from 0.1. If we copy this. Put this next to this one. It's only to give you an idea what is actually meant. So basically we said we had like initially we had the profile at minus 100 centimeter matrix potential. So basically the moisture content at minus 100 centimeters. So this is plotted in absolute values. Is close to 0.25, so 0.24%. So this is how it starts out. And then basically it saturates the profile until it gets to the saturated water content. This is at 0.4 something. So this is basically this upper limit. So this is 0.2426 is equivalent to minus 100 centimeter matrix potential, and then it goes all the way up to saturated condition. But of course, when you infiltrate initially, so the infiltration process, when the soil is dry, you actually have a lot of slopes. So the infiltration rate is actually initially high, so the flux is high. And then as the boundary layers close to the surface get wetter and wetter and wetter, it kind of slows down. That's the reason you basically see like the decrease in surface flux until it stabilizes. This is basically what this tells us. Does everybody understand this approximately what's going on here? So we're basically starting a system where I have a partially saturated soil, and then I apply water at the soil surface. So water starts infiltrating, changes the moisture content, of course, first in the shallow depth at 26 centimeter, and as water propagates further down, it starts changing the moisture content in 50 centimeters. So this is what those two curves show, and we basically start from the initial moisture content, because the profile was at minus 100, uniformly minus 100 centimeter matrix potential. We start with the initial moisture content of 0.24, so this is basically what this indicates when we look at the soil water characteristic. And then we basically go up all the way to full saturation. We also could plot the cumulative, so this is the actual. To see how this actually behaves, you can also plot the cumulative surface flux. Maybe we go to the spillable file again. So there should be something summary. Top. Oops. Delivered file likes fixed increments.
You want the sum beta?
Yeah, but I didn't, the spacing was twice. there should be so we cannot see it very well, but you actually see like a steeper slope, so higher flux initially, and then it kind of slows down to a constant flux. So if you plot this from so basically see initially you have like a steeper slope, which means that actually more water is entering, and then you basically see like the linear. This is basically exactly what is also shown in this one. So you see like higher actual surface flux in the beginning, and then it reaches a kind of constant value. This basically once the soil is saturated, and it really get any cannot exceed like saturated hydraulic conductivity. It's basically then it infiltrates exactly at the rate of the saturated hydraulic conductivity. So okay, let's move this out. This is our oops. Does everybody have a little bit more time, like 3-4 more hours? Here demonstrating this stuff is actually for everybody to follow. It's kind of time consuming, but I think it's good if we go through this step by step, but also see look at logical explanations right away. But this is really one good thing with HYDRUS. It's
again, why didn't you put it on the same graph? Why didn't you plot this thing on the same?
You can plot it on the same graph.
I thought there is a reason.
Yeah, there is a reason, because when we look at all this, then you lose all the detail here, because if we set this one back to the set this one back. You see, because here we have like scale from 0 to 30, so you would lose all this detail. This was the only modification. But you can plot it in the same graph, so that will matter. So now let's separate this and then go to the problem 2. Open this stuff. Problem 2. Material, so problem 2, we only want to repeat one, but now we actually want to change the initial conditions. We want to make the soil a little bit drier. So instead of starting with minus 100 centimeter matrix potential, we want to start with minus 330. So everything else is actually the same. So let's go actually all those files. Then we go back to HYDRUS, we close this one. And then what we really want to do, so because we want to keep all this, we want to kind of save this as a new project. So only save like, take project 1 or problem 1, save as, then only give it the name project 2, P02. Then the only thing we actually want to do, so we want to keep everything exactly the same. We only want to go into the graphical editor and change the initial conditions.
Oh, no.
So we want to edit conditions. So the first thing, we want to change everything uniformly to minus 330 centimeter. 330 centimeter is usually often affiliated with field capacity. So this is the matrix potential after internal drainage. So if you wet up the soil and you have internal redistribution, then usually we assume like approximately minus 330 centimeter. Then we change this, so we want to have uniform 330 minus 330 centimeters of the soil profile. Okay. And then I only go back again one more time, edit condition, and I put, because we want to have like constant pressure on the top, so I put the very top down to 0. Completely the same like we did last time.
Oh yeah.
So the only really difference is now we start out with a slightly kind of drier soil profile. We say save changes, okay. And the only thing is we need to run, calculate, execute HYDRUS, okay. And then we only put all this information. So now we basically again open the observation node output file. Exactly the same thing now, only for a different simulation. Here it's actually to separate the lines which we've used to limit it, and then have a separation at the space of common finish. And now we have time. Level file. Then you say we want to copy the actual boundary flux on the top. Then we also want to copy the summary. we basically only want to compare problem 1 and problem 2. So we only add select data. So now we have 26 centimeter problem 2. That's where we get the 150 centimeter. One thing is definitely the advantage if you practice a little bit how to use Excel efficiently. Hey, don't give up, follow, focus. That's the, this is it's only copying data from file to file. Nothing. So now when we look at this, so we started out with a little bit drier kind of initial conditions. So that basically means the moisture content initially for the second case is lower. So again, if you would go to 330, which is approximately here, to get around 0.18, so it's approximately 0.17, approximately here. Then it reaches, of course, like 26 centimeter. It wets it completely up, and then it basically reaches 50 centimeter, and it wets it up. Then we can add either one of them, cumulative or surface flux. Let's edit this one first. So we actually only should see a little bit difference initially. I mean, there's actually not too much. So if we would zoom into this one, we actually would see that for case 2, it's
Sorry, I'm visualizing. Sorry.
visualized.
Sorry about that.
So we can zoom into this one to see the difference. So you see there's a slight difference in the kind of response time. So the initial one is a little bit steeper, so it goes a little bit faster. which is actually strange because you would expect the opposite. Because the drier the soil, the higher the initial one. This is the, let's see, this has got the right. Oh, now we need actually to look at this differently. This is the actual flux. So it's actually higher for the case 2. So you see, case 1 it's around -9. At case 2 it's higher. Then it ramps up until the surface is completely separated, and then basically it stabilizes. So is everybody that far? Should we wait?
Yeah, hang on. Give me 2 minutes.
Okay. It's really only a matter of kind of copying things from the observational file to the Excel file, graphing it, and then from the tuller file to the Excel file, graphing it. One thing that always confuses people and me is the sign convention. So flux going into the soil profile is negative, and flux going out of the soil profile is positive. That's the reason this was a little bit confusing. But only in terms of talking about the theoretical aspects of infiltration, the drier the soil, because of sorptivity, the higher the initial infiltration rate. And then of course it kind of increases until it reaches the saturated hydraulic conductivity. And then there's no way for, it cannot really exceed the saturated hydraulic conductivity. So this is basically the limiting factor. This is when everything is saturated, then it basically levels off and remains constant.
Can we keep going? Because I have a meeting.
Yeah, we do one more, and yeah, this goes much slower than expected. But for us to move on, you need to be focused and you need to practice this stuff a little bit. This, I think, is very, very important to make this successful, because if we spend so much time copying things around, those are really it's only manipulating, like opening files and manipulating and transferring data. So let's do one more, and then we'll probably spend most of next week to finish this problem. You can look at it. I mean, a lot of those things, they are basically progressing step by step. At a certain point, you're going to run into some troubles. I think step 5, where we need to play around a little bit. But the next problem is basically now we have exactly the same setup. We have initial condition, like in the first problem of -100 centimeters throughout. Now only we want to change from a constant pressure head top boundary to a constant flux boundary. And the constant flux that we want to apply should be equivalent to the saturated hydraulic conductivity. And when we go to HYDRUS, let's save this file, save as problem 3, problem 03. So now when we go to soil hydraulic parameters, you basically see that the saturated hydraulic conductivity is 1.04 for long. And this is exactly the flux that we want to apply, that we want to force onto the system on the top. So the only thing we actually want to change is, so I cancel this, only to see that this value. The only thing we want to change is the boundary condition. So now I want to switch from a constant pressure head to a constant flux boundary condition. And then when we go to next, we actually need to specify the flux. And here we say it's equivalent to the saturated hydraulic conductivity. So we say 1.04 centimeters per hour. The only thing is, need to be really careful, because this is a flux that is actually going into the soil profile. We need to give it a negative sign, because otherwise this wouldn't, first of all, it wouldn't converge, and it wouldn't really kind of model infiltration. It would kind of model evaporative flux. So we need to put the negative sign here and say OK. Then I only need to go back to the graphic editor, and so I want to change this before we run it. Yes. And I want to change back the initial conditions to -100 centimeters. Since we impose a constant flux, so we don't need to do anything with the top boundary. It's really only when you have, like in 1D, when you have a constant pressure boundary, you actually need to specify it together with the initial conditions. But now we say, like, the soil profile is the moisture content equivalent to a potential of -100 centimeters. And then the constant flux boundary conditions, we say that the flux that should enter on the surface should be 1.04 centimeters. per hour, which is equivalent to the set hydraulic conductivity of the slump soil. And say, okay, yes, yes, and we only need to run it. Then again, we only copy those files. So she already set this up. Problem 3, material down. Initial condition is minus 100 centimeter pressure route. Boundary condition top is constant flux. Actually, we should put minus here, that we don't get confused later. Bottom is with drainage.
When it says the numerical solution has not converged, means something wrong.
So that means you didn't input the flux with a negative sign,
Okay.
if it doesn't converge. Because I think mine converge, the other two wrong. Yeah, it's converging.
So why it doesn't converge if it happens?
No, because when we do the opposite with dry soil and then we apply a relatively high evaporative flux, then we have this big gradient. So he only didn't convert because he didn't kind of specify the flux with a negative sign. See, basically what he did was imposing evaporation instead of water running into the soil profile. So really, if you want to copy this at once, you only go to Shift, then you put the End and the arrow down button. Then you go back up. Then you push the Control button, then you kind of mark the beginning of the next line. Then you again push Shift and downwards button. Then you go all the way back up. You push the Control button, Shift and downwards. This is like basic Excel functionality. Now we basically copy all 3 columns with one shot. Copy. And then again we can open the T-level file. It's always good to use delimited, next, and then use tab and space. Then I think it's separated to right. Yeah, then again we can kind of take the time and do the same thing, Shift and downwards. Go back up again. Stop. Well, now we have a flux. If we have a flux, we actually want to kind of look at the pressure distribution based on the instruction. So we want to plot actually H top. Because the flux wouldn't tell us a lot because it's a constant flux, so it's always minus 1.04 centimeter per hour. So, yeah, this is not so we basically want now look at the pressure distribution at the top. The only thing we want to do is we can take this chart, because now we want to basically compare one and three. So we have one, so we only change actually this one. We can only move this to 3. Then we take this one. We move it to 3. So what do we see now? Of course, like initial, because the initial moisture content is the same, so we start at the same level. But you see a difference in time, because the flux is obviously different. So the first one stabilized at 1. So here you actually see a little bit kind of, when we have like constant flux pump, we have 1.04 centimeter. We actually see a little bit later arrival time, because the flux initially, when we compare it to this one, was actually much higher. You see, now we have minus 1.04 throughout, so it's a little bit different. And then we can plot the pressure distribution on the surface. So basically, until it's saturated, we have negative pressure. So we start out with minus 100, a little bit below. Then, as water enters, it gets more and more saturated. We get to 0 pressure. And then you actually see something quite interesting. What happens here? So this now is the pressure on the top conduit. You see that it exceeds 1 at certain times.
This water could.
So it actually our flux, or the flux that we force onto the system cannot really enter the system. So there's always a little bit of water buildup. But and this is actually when HYDRUS starts having problems with convergence. So if you only quickly go back, so here we don't, this is basically the same thing if we would remove water from the system. So it increases the pressure head, so that means actually water is bonding and is gone. If we now increase this, when we go back quickly to one more run with HYDRUS, and when we go back to the this boundary condition, and we change this double, so this would be like example 5. So if we double this 2.48, we say okay, and we leave everything completely the same now. It's not going to converge. So if we execute HYDRUS now. So now it basically tells us numerical solution has been stopped since it had not converged in 10 consecutive time steps. But we are going to deal with this, I think, next time, because everybody looks already quite exhausted. But really, practice Excel, so it shouldn't be any issue for anybody to copy kind of data from one file to another one and graph things in Excel. Because we actually want to do quite a few. I mean, the major idea is to understand how to actually handle HYDRUS, and also how the system actually behaves. To get the theoretical background, to get hands-on training with HYDRUS. So dealing with Excel and all these things, everybody should know. If you don't know, practice. Spend a little bit of time and try to practice this stuff so that we can move through those things a little bit faster. And look at this. This story will take us a good portion of next week to go through all of those examples, because it gets a little bit more complex with every step. But by doing so, we actually understand this system. So in the end, I think everybody understands the situation if this works quite well. And then we also want to do this very similar simulation with HYDRUS 2D and see what the difference actually is between HYDRUS 1D and HYDRUS 2D. So maybe next week probably we skip the PowerPoints and we start working, and if there is time in the end we look a little bit at theoretical stuff. But really practice this stuff. I think if you wait always until the very last moment, also with the homework assignment, because last week we basically step by step really went through everything, and the only difference was to basically now model exactly the same thing, only for a different soil. This shouldn't cause any troubles, and I think if you do this immediately, it's also much easier, instead of waiting until the next Monday and then kind of have to restart and rethink all those steps. So this course requires a little bit of practice at home. It's not only like in class. I already make it as easy as possible. Going through those kind of problems really as slow as possible, but you also need to progress at least a little bit. Because we want to get to the really interesting part, working on like projects in a couple of weeks, 2, 3, 4 weeks. So are there still any questions with regards to the second homework? Yes, no? Maybe? we continue with over the 4 next week. But try to look at this, it's really only a little bit of manipulation. So I'm sure you for sure should be able to do number 4, number 5, because it's more not going to convert, it's going to be a little bit more tricky, but you can play before those things that we mentioned in the end. First increase the spatial discretization, then look at time discretization, iteration limits, and if you still cannot get it to work, then there is another trick. You can